A particle is performing undamped oscillations due to electric force with coefficient k. So for our convenience, we'll just replace this electric force with a spring coefficient k, just like that. Now when the particle was in equilibrium, a permanent force F was applied to it for tau seconds. So this electrical force with coefficient k, like we said, it's just like a spring. So initially the spring was not stretched. And then a permanent force starts applying to it for tau seconds. Find the oscillation amplitude and the particle acquired after the action of the force ceased. And draw the plots of x versus time. So this whole situation is analogous to, let's say, initially the block was here and the spring was unstretched. And let's assume that suddenly F is equal to mg starts to act on the mass. Just a hypothetical situation, so you can visualize what's happening. So initially the spring was not stretched, and then at t is equal to 0, a constant force starts to apply. So let's say gravity starts to apply on the mass at t is equal to 0. So you can imagine the particle will just do SHM about this mean position. And the mean position we know is given by this F is equal to kx. So mean position will be at F by k. So it will just keep performing SHM like that. But then it is given at tau seconds, the force ceased to exist. So again, you have to just visualize that the particle is performing SHM like this, and suddenly gravity ceases to exist. So what will happen after that? So you can imagine that if gravity suddenly stops to exist, then the equilibrium position will become this again. So the particle will start performing SHM about this point. So again, initially the particle was here, the spring was unstretched, there was no force, so particle was at rest. Now suddenly force starts to get applied, so the particle will start performing SHM about the new mean position. So it will just keep doing it until it suddenly stops. And when it stops, again the equilibrium position will shift to this position, and the particle will start to perform SHM about this mean position. So this is what is happening. So we need to find what will be x as a function of time. So let's break this whole motion before tau time and after tau time. So before tau time, F is there, and after tau time, F is not there. So before tau time, as discussed, the particle will just perform SHM about this mean position. So you can see the equation of SHM will be amplitude 1 minus cos omega t, because we are taking this as x equal to 0. So mean position will be x equal to f by k, which is also the amplitude, and maximum it will go to 2f by k. So in the phase diagram, you can see the particle is here initially at x equal to 0, t is equal to 0. A amplitude is f by k. So our standard equation is x minus x mean is equal to a cos omega t plus phi. So since we are taking cos, phi is taken from here and cos is pi. Omega will be root k by m. Amplitude will be f by k, and mean position is also f by k, which gives this equation. So we are familiar with how we get this equation if a particle is just dropped from rest. Now after tau time, force stops to exist. So the mean position shifts back to x equal to 0 here. So our new equation of motion becomes x minus x mean. So this standard equation, x minus x mean is equal to new amplitude into cos omega t minus tau plus phi. So here we are talking about t greater than equal to tau. So we are only counting seconds which are more than tau. That's why the term t minus tau. So after tau time, let's say after 1 second after tau time, so this becomes, t will become tau plus 1. So this whole thing will become omega into 1. That's what we want. So we are shifting the time to tau. So x minus x mean is equal to a dash cos omega t minus tau plus phi. And let's differentiate this equation to get this. Now between the two motions, before tau time and after tau time, So we have that overlap at t is equal to tau. So obviously with this equation and this equation, at t is equal to tau, position should be same and velocity should also be same. Position and velocity both cannot change abruptly. So we'll just compare these two equations. So comparing 1 and 2 at t is equal to tau. So they should give the same x and same x dot. So at t is equal to tau, x is this, f by k 1 minus cos omega tau. And from here, x is, so when you put t is equal to tau, this will become 0. So this will become cos phi. So this becomes a dash cos phi. And similarly, when we equate x dot, so x dot here will be f by k into omega sine omega t. So when t is equal to tau, this becomes f omega by k sine omega tau. F omega by k sine omega tau. And x dot at t is equal to tau is minus a dash omega sine phi. Minus a dash omega sine phi. So we have these two equations. And because we need to find amplitude, let's not bother about phi. So let's get rid of phi by squaring and adding. And we get f by k whole square 2 minus 2 cos omega tau is equal to a dash square. And from here we get a dash to be 2f by k sine omega tau by 2. So this is the new amplitude. Now when we are going to plot the graph, just again try to visualize what will happen. So initially, like I said, the gravity starts to exist, and because of that the particle will perform SHM like that. And depending on where the gravity stops, you can imagine what will happen to the SHM. So let's say the particle was here and then gravity stopped. So new equilibrium position is this. So now you can imagine the particle will perform SHM with this whole thing as amplitude. Now again, let's say the particle was here and then gravity stopped to exist. So obviously particle will stay here. So it will not perform any SHM. And if gravity stops somewhere in between, then the particle will perform SHM again about this axis, about this equilibrium position, but its amplitude will be less than this maximum amplitude. So make sure you understand this, and so you are able to visualize what's happening. So then it will be easy for us to plot the graph. So let's see the graph now. So let's see the graph. So we are just plotting these different graphs for different values of tau. So here the green curve represents the position when the force was there, constant force was there. And this yellow represents that when the force stops to exist. So that happens as tau time. So before tau time, the particle will follow green line, and after tau time, it will follow yellow line. Same here. So before tau, it will follow green, after tau, yellow. Before tau, green, and after tau, yellow. Now green line, you can see here the particle is performing SHM about its mean position, which is at f by k. So just like here. And after tau time, when the force ceases to exist, the particle will perform SHM about its new mean position, that is x equal to 0 here, which we discussed that once the force stops, then the mean position shifts to x equal to 0. So it will perform SHM about this point. So that's what this represents. This green is the mean position of the green path and yellow is the mean position of yellow path, which does not change. It doesn't matter what is tau. Tau, however, changes the amplitude. So we just saw that the new amplitude is 2f by k sine omega tau by 2 here. And we can see that depends on tau. Time period of SHM is, however, same as before. So for green and yellow, both the time period is same. So you can see that both are having same time periods. Third thing is, and that time period is 2 pi by omega, where omega is root k by m. because a constant force does not change the time period. Third point, x and x dot, so x dot represents the slope. So position and velocity of the particle will be same at tau for both the graphs. So that means wherever these graphs overlap, there, of course, since they are overlapping, position will be same, but also slope will also be same because velocity cannot change suddenly. So here both the slopes have both the graphs have zero slope. Here again both have zero. And here you can imagine that the slope of both green and yellow graphs is same. That means velocities are same. And because they are intersecting, that means positions are also same at tau. So now I think it's easy to plot what's happening. So let's take different values of tau. So first let's take it when sine omega tau by 2 is 1, which gives our maximum amplitude. So you can see that will occur when the force stops acting here, when it has reached its maximum position. So in this case, when the particle has reached its maximum position, that is 2f by k, then the force, if it exists, then the amplitude will be maximum of the new SHM, and that amplitude will be 2f by k. So that new amplitude will be 2f by k. Second is amplitude will be minimum, that is 0, when sine omega tau by 2 is 0. Which means the force will stop to exist when the particle returns to its mean position. So when the force was, sorry, I don't mean mean position, when the particle reaches its initial position, when the spring was unstretched. So the particle is performing SHM like this under gravity, let's say. So when the particle is here and then gravity stops, then the particle will stay here because spring is at its natural length. So that's what will happen. The particle is performing SHM like this, and if it stops here, then the particle will stay there. So it will not move further. Third is any other time. So these are the two extremes, when the amplitude is maximum and when it is minimum. Any other time, amplitude will be between 0 and 2f by k. So here the amplitude of the particle is 2f by k, here it is 0. And if the force stops to exist at some random point tau, so there you can imagine, if you just draw the slope that is similar to the original slope, so the resulting amplitude will be less than the total amplitude of the maximum amplitude of 2f by k, and the particle will start performing SHM like this. So in all the three cases, the mean position of the new SHM is still this, mean position of the old SHM is still this. So the graph will be like this. All right.